the Yarra Valley, as well as from KC and other parts of Melbourne. And indeed, I'd like to welcome Dr. Tim Standish, who's joining us live from California. Dr. Standish, we are very glad that you are with us to present to us this afternoon, which is, I understand, Friday evening your time. So thank you for being available to us.
It's more than my pleasure.
These channels are being, some of these feeds are feeding into wider channels through Facebook Live and other places. So I would like to welcome everybody who's watching. So this presentation will have a question and answer component at the end. I understand you're happy to take a few questions, Dr. Standish?
Very happy, yes.
Great. So without further ado, I'd like to give it over to you. And Dr. Standish is a scientist who is joining us from America, and he's done a lot of research into environmental science and other fields. And he is part of the Geoscience Research Institute that is based in Loma Linda, California. So thank you, Dr. Standish. We look forward to hearing what you have to present to us.
Well, thank you very much. Yes, I'm excited to be in Loma Linda right now. We had a real milestone over the past week. We have a large hospital here, and actually several hospitals in this area. And for the first time since last April, we had a day where there wasn't a single COVID patient in our ICU unit. So that was a very exciting milestone for us, because things have been pretty bad here. Obviously, I see this as being one of those situations where science has really made a positive difference in the world. And obviously, there are endless other examples of that we could come up with. One of the great things about science is people are out there looking at stuff, figuring out stuff, finding new things all the time. And every week there are thousands of very carefully researched science papers that make it to publication. Obviously, that doesn't mean that they're all correct. There are plenty of papers that are published, not fraudulent or anything like that, but occasionally things will get published that turn out not to be correct. It's just the nature of the way science works. But still, it's very exciting to try at least to keep up with the scientific literature. No one person can do that. So what I'm going to present to you is sort of three papers this afternoon. And I should tell you that I should probably confess this right now. If you read the abstract that I sent, I lied. I'm sorry. There were just one or two other papers that came along that were so exciting to me. I thought, no, if I'm only going to choose three, which is probably for the best, because otherwise we could talk, pretty much forever. I'm going to go for these three that actually came out here in the last couple of weeks, basically. So let's launch into them. I've made every effort here to summarize these papers as accurately as I can, but just bear in mind, if you happen to have a PhD in one of these areas, yeah, there are going to be some things that are significant simplifications and cutting down of the information that's there. But I'll try to provide enough information so that you, if you are interested, can go and look at these papers and get into the deep technical issues that many of them represent. So let's see here. Here we are. I've got the presentation here, and I'm hoping everybody can see it. So I've entitled this 3 2021 science papers worth thinking about. As I said, actually, I could have said 3 papers that came out in the last week or two. That would have been the case. This has been a bumpy year, really, for papers that relate to how we think about the creation. I haven't tried to find, that definitive paper that will prove it to anybody who doesn't want it, but I have just included these 3 because I found them interesting and I found them informative as we think about these things. The first of these, and let me also stress this, these papers are not published by people who agree with necessarily the meaning that I get out of them. Okay, so that's important to bear in mind. In fact, these would be papers that are produced by people who would, in general, be quite dedicated materialists and believers in the materialistic theory of evolution in general. So the first one is this. The title of it is Cone Mitochondria Act as Microlenses to Enhance Light Delivery and Confer Stiles-Crawford-like Direction Sensitivity. Now, I'm going to take a big step back to give you just a little bit of background on why I think this is an important paper. And if you've done things at the church there previously, I'm pretty sure I presented some of this information. So some of this at first will seem like just review, but you'll see why that review is important as we get into the details, or a few of the details of this particular paper. And so first of all, let me start with this fabulous quote from Richard Dawkins. I should tell you again, you know what? I greatly value Richard Dawkins. I enjoy his writing, and I appreciate the fact that he says exactly what he's thinking. He's not trying to dance around issues and things. So that gives readers an opportunity to evaluate the strengths of these arguments that are being made in support of the Darwinian view that he embraces. He wrote in a book called The Blind Watchmaker, suppose I tell you that the eye's photocells are pointing backwards, away from the scene being looked at. The wires, that would be the neurons, the nerve cells that are carrying the signals in your eye, the wires connecting the photocells to the brain run over all the surface of the retina, so the light rays have to pass through a carpet, a carpet of, where am I? So light rays have to pass through a carpet of massed wires before they hit the photocells. That doesn't make sense, and it gets even worse. So let's look at what Dawkins is putting forward here to try to make the argument that whatever designed, if you want to use that word, the eyes that you find in vertebrates, There are other kinds of camera type eyes out there, so just keep that in mind. But vertebrate eyes, it did a terrible job. And that's what he believes. He believes that because the theory of evolution that he subscribes to doesn't allow for any intelligent input into the process, that means that you would expect bad design. And here he's saying the bad design is obvious. The whole retina is backwards. So let's take a look at it. And that obviously has implications. So here's a human eye, or it could be pretty much any other vertebrate. And at the back of the eye, you have the retina. That's where you find a whole lot of light sensitive cells. And of course, there is a lens in the front, so it takes any images that you're looking at and focuses those images on the back of the eye, where those light sensitive cells respond to that light. And that would be pointless if there wasn't a way of taking the signals that are generated there in those light sensitive cells to your brain. The problem, as Dawkins sees it, is that the nerves that carry those signals run in front of the light sensitive cells, not behind them. So they get in the way. So let's zoom in here on the retina and just see what he's talking about. So here is a section of the retina. Here we've got our light detecting cells, and you can see the light is coming in from above in this illustration. Now, one of the things that you have to bear in mind about these light sensitive cells is that they are very metabolically active. That means they use a lot of energy and they create a lot of waste. In the human body and in the bodies of other vertebrates, the fuel to keep a high metabolic rate going is brought to cells via the bloodstream. And waste products are carried away via the bloodstream. So it is absolutely necessary that there be a very efficient blood carrying system to bring blood in and carry the blood away from these light detecting cells. The problem with blood is light does not pass through blood. So thankfully, the blood is behind these light sensitive cells. However, that means that the nerves have to go somewhere else. They can't be where the blood is because two things can't occupy the same space at the same time. So the only place to put those nerves is in the front. Dawkins' complaint is that when light is focused on the retina, it is going to get dissipated as it passes through all of those nerves, even though they're pretty transparent, and there'll be a loss of clarity as a result of that in the eye. Now, this is sort of an engineering necessity, so it's a little bit harsh to criticize, whatever it was that produced the retina for this, because things really, because of the way vertebrate eyes operate, it wouldn't really work to have the blood in front for obvious reasons. So anyway, but he's quite harsh in his evaluation of this. Whether it's fair or not, I guess is up to you. But he goes on and he says, one consequence of the photocells pointing backwards is that the wires that carry their data somehow have to pass through the retina and back to the brain. So this is a second problem that is caused by having all of those nerves in front of the light sensitive cells. They've got to go back somewhere through something to the brain. So then he goes on. What they do in the vertebrate eye is all converge on a particular hole in the retina where they dive through it. The hole, filled with nerves, is called the blind spot. It's not just bad design, it's the design of a complete idiot. Well, I've already explained why it has to be this way. So I'm not sure that it, just based on what Dawkins knew when he wrote this, it's really fair to say it's the design of a complete idiot. It's just the way it has to be. But let's see, is there a blind spot in the human eye and in that of dogs and other vertebrates? Yes, there is. So there you can see there's the optic nerve going through. It goes through that layer of light sensitive cells. If there's no cell there to detect the light, obviously you're not going to see anything there. So what's going on with this? By the way, you can look. You can test to see whether you've got a blind spot. I can guarantee that you do, basically by making a plus and minus sign like this on a piece of paper, and then you cover one eye. In this particular case, I'm covering my left eye, and I'm looking at the plus sign. And right from where I am, as long as I'm looking at the plus sign, I know that there is a minus sign over there to my right, but I just can't see it. If I look over there, it's there. But when I look back at the plus sign, it's not there. If I move my eye back and forward, the light that's coming from the minus sign starts hitting areas where there are light sensitive cells. But yeah, there is a blind spot there. And you do the opposite. Let's see here, right about there. When I'm looking at the minus sign with my left eye, the plus sign is vanished, at least for me. I'm about, I don't know, 18 inches or 45 centimeters away from my screen as I'm doing that. If your screen's a little bit smaller, you may need to get a little bit closer or further away. So yeah, both of our eyes have blind spots, but there is some good news about that. And that is, fortuitously, this doesn't affect most people in any way because we have two eyes. Seeing as we have two eyes, what we can see is almost 180 degrees. And where the blind spot is in my right eye, there is not a blind spot in my left eye. So my brain is taking that and putting in the information from my left eye where the blind spot for the right eye is, and it's putting it all together. There are no blind spots there, actually. The only people who really have a problem with this would be, I don't know, pirates or something with their, missing eyes and patches over their eye and whatever. Yeah, someone with one eye may have an issue with it, but even they're moving their eye around, they should be able to see 100% of what that eye can see pretty well. So yeah, it's an issue, but it's an issue that obviously there is a very elegant engineered solution to. So let's get back to this business, though, of the light being dissipated as it passes through that layer of nerves. This is something that Dawkins wouldn't have known about when he actually wrote those words. It turns out that there are these special glial cells. Glial cells are just a class of cells that are associated with nerves. These ones are special glial cells, and they pass through the network of nerves and act as fiber optics. So what happens is the light comes in and it is carried through to the light sensitive cells without that dissipation of the light and reduction in the clarity and resolution that we should be able to get. That's pretty amazing. And it turns out your eyes are doing this, all the time, constantly as you're watching this particular presentation, but anytime your eyes are open, this is how things work. I personally wouldn't call this the design of a complete idiot, but there you go. That was certainly Dawkins' opinion at the time. Let's, however, remember he said the whole thing was backwards, and in one sense he wasn't exaggerating about that. So we're going to just zoom in a little bit on these light detecting cells themselves. What happens once the glial cells carry the light to them? Now, there are a couple of different kinds of light sensitive cells. We're just going to look at one kind. These are called cone cells. And these are the kind of light detecting cells that we find right now center of vision. They are the ones that pick up color best as we go towards the edges. Even though we think we're seeing color all the way around, we are seeing a little bit of color there. There are cone cells as we get into our more peripheral vision. They're a little bit different. There are a few, I'm sorry, I should have said rod cells. There are a few cone cells mixed in with them, but the cone cells are more concentrated towards the center of our field of view. And anyway, so this is what one of them looks like. They sort of look a little bit cone shaped there at the bottom, and that's apparently where they got their name from. Up at the top, you see the interface between the cone cell, this light sensitive cell, and the neuron cells or the nerve cells that are going to carry the signals generated in this cell away and back to your brain. There's actually a little bit of signal processing that also goes on in your retina before the signal is sent on to your brain. It's a pretty elegant and amazing thing. Then there's this inner segment that's the main cell body, and that's where you find the nucleus and mitochondria. We'll come back to that in just a second. Then there's the outer segment, and the outer segment is where there are special pigments that absorb certain wavelengths of light. That's why these can differentiate between different colors, because different kinds of cone cells have different pigments that absorb different wavelengths of light. Now, yeah, these mitochondria that are in there, remember how I said that these cells are very metabolically active? Mitochondria are basically the energy factories, the generating plants of the cell. And because there is so much metabolic activity, so much energy that's being used by these cells, there are a lot of mitochondria in there. But there are other, obviously, all of the organelles that you find in other kinds of cells as well. So let's see what happens here when light is transmitted into one of these cone cells, or at least let's think about it just a little bit. In comes the light, and it's going in, and obviously because I drew this, I can make it do anything. But in real life, what you're seeing here isn't what's going to happen. In real life, what's going to happen is, or at least in theory, what should happen is as that light comes in, it's going to be refracted off the nucleus and off the mitochondria and just get scattered all over the place. I don't know whether you've ever looked inside a camera, but if you've ever looked in there, you probably noticed that it's black. I don't think I've ever seen anybody try to put white inside a camera. The reason that it's black inside the camera is because light, stray light going off in every direction would cause the image that is focused on the, either the, the light sensitive surface, let's just call it that, either film or, or whatever it is, that, if you've got stray light flying all over the place, that's going to be picked up by the sensor, and you're not going to get a nice clear picture. It's going to be a little bit of a mess. So imagine if light was going into these cone cells and being just sort of scattered all over the place. That would then be picked up by other cone cells, and you'd have all kinds of problems. So how is that avoided? I'm just going to show you one of the ways. That's what this paper talked about. One of the ways in which that is achieved. Keeping in mind, the light has to come in, get down here to the bottom to these outer segments, and a signal is going to be generated there, and that signal is going to be sent back up through the cone cell to the neurons that are going to carry that signal back to your brain. It's amazing to think this is going on right now while you're looking at this. The big question then is, how is light efficiently transmitted to the light absorbing pigments at the back of cone cells? How does that happen? That's what this paper that just came out addresses. So remember these mitochondria, the energy factories of the cell. There have to be a whole lot of them because the cell has very high energy demands. But it turns out that they are not kind of randomly arranged inside the cell. That's in most vertebrate cells, they are arranged kind of randomly all over the place inside the cell. But in cone cells, they are arranged into a bundle. Okay? That forms a micro lens inside the cell. It's absolutely incredible to imagine that you could do this with mitochondria, but this paper does a spectacular job of showing how, well, not just theoretically how this might work, but showing that it actually does work to work as a lens to focus that light. So as the light comes in, yes, it might start to spread out a little bit and stuff, but that micro lens catches it and bends it and focuses it down into the outer segments where the pigments are that are going to absorb that light, so that the light is used pretty much as efficiently as it could be. And it's not flying around all over the place making a blurry picture or anything like that. I don't know, when I saw this, I was absolutely amazed. I don't think I'm unusually easily amazed by things, but this is so elegant, and it all works together in such a fabulous way. I hope that you're as thrilled with it as I am. Anyway, here's a quote from the paper. They say, "We demonstrated that spatial organization of cone mitochondria allows the mitochondrial bundle to efficiently concentrate light to enhance inner segment, outer segment coupling." And Yeah. I mean, just absolutely amazing how our bodies work. No wonder our eyes are so good. And yet, another paper that came out this year with an ironic title, in that the authors make this comment: consider eyes, organs so complex they fool some into thinking they must have been designed by a creator with a lower C, interestingly enough. Wow, seems pretty bold. Uh, when when you look at something and it looks designed, why would you think you are being fooled? Or are you fooling yourself when you look at something that looks designed and telling yourself it isn't? So what are the implications that I see, at least, of this particular paper? Well, first of all, this is not the first and will probably not be the last case where proofs of Darwinism become progressively less compelling as new data accrue. In fact, this is a pattern that I personally regularly see. Many of those things that were presented to me as compelling evidence that Darwinism was true up through graduate school, many of them have sort of been abandoned. And it's interesting to me that the eye has not been abandoned. It must take some incredible faith, really, in your belief system to continue believing the way Darwinists do. Because Darwinism is as much a religion as Catholicism, Hinduism, or animism, I think especially animism, believers will commonly simply continue to interpret the evidence within their old worldview, perhaps not even seeing how clearly misplaced their beliefs actually are. And to me, this paper kind of demonstrates that very nicely. And let me just stress here, this certainly doesn't mean that anyone has all the answers. I have to say this because it does feel like every church I go to, there's at least one person who does believe that at least they know all the answers. We've got to be careful. No, we don't know everything. Christians do not know all the answers any more than anybody else does. Everyone lives by faith, but the faith of Christians does seem to have been richly rewarded. And that's certainly the way I feel through my career as a scientist. So here's another demonstration that I'm a terrible liar. I said 3 papers, but I'm really sort of bundling these 4 papers into one. I hope that you won't be offended by that. The top 3 papers were all published together a week or so ago in the journal Science. And the one there at the bottom is on the same topic, but published in a different journal. And I will not read all of the titles here. I'll just read the top one: Non-canonical DNA polymerization by amino-adenine-based cyphoviruses. I think it's cyphoviruses. So I know that sounds a little bit like a foreign language, but basically, when we talk about molecular biology, there are certain central principles that are generally accepted there. There's even something called the central dogma of molecular biology. There is something different from the canonical, from the normal way in which DNA is, that is going on in this particular group of viruses. And it turns out that this is more widespread than was initially thought. This phenomenon was first observed about 40 years ago, maybe a little longer, about 40. No, it is a little over 40 years. But it wasn't followed up on. So let's have a look at what it is. And again, I'm going to give you a little bit of background that will help you understand what I'm talking about and why I think it's philosophically important. Here's Richard Dawkins writing again. He says, "The genetic code is universal. I regard this as near conclusive proof that all organisms are descended from a single common ancestor." So what he's saying is that language, that code, I should say, that is used to encode information in your DNA is the same as the code that is used in the bacteria that live in your gut. It's the same as the code that is used by platypuses and gum trees and mushrooms. They all use the same genetic code. And he's saying, hey, you know what? The fact that we see this in every organism out there, and it's the same, indicates a common origin, and that origin is descent. So basically, we can trace the origin of it all the way back to a single common ancestor of all living things that happen to have this code that it used to encode its information. There are certain philosophical problems and with that argument, and also with the there are certain alternative explanations that might explain this, but the problem here is multiple. One of them that we'll get to is that the genetic code, in fact, isn't purely universal. This is what he's talking about. This is the universal genetic code. And these letters of the alphabet, every word in the genetic code is only 3 letters long. And those letters are spelled, or those words are spelled with 4 chemical letters that we symbolize as U, C, A, and G. These are the letters that are used in RNA. If we're talking about DNA, the U is a slightly different chemical that's symbolized with T, but U and T behave in pretty much the same way. And so this is the code written out in RNA. And you can see here, for example, if you have 3 U's in a row, if you just look at the top left-hand corner of this table, if you have U, 3 U's in a row, in the code, that spells out the amino acid phenylalanine. And proteins are made by joining together amino acids in very specific sequences to create these proteins that are obviously very important when it comes to our bodies and the bodies of everything else. So Dawkins' claim was that this is a universal code. The problem is there is variation in there, but let's just go through this slide. Lack of variation in codon meanings across almost all phyla is taken as an indicator that initial assignment must have occurred early during evolution, and all organisms must have descended from just one individual with the current codon assignments. It's generally recognized that evolving codons or a code particularly the way that the genetic code works, would be close to impossible. So somehow or other, this code that we have, according to the materialistic kind of Darwinian view, it just got locked in by chance, and that's what everything happened to inherit. There are some big problems with that idea that we're not going to really go into. One of them is that the genetic code happens to be fantastic. If it happened by accident, well, that was an act of good fortune that was quite remarkable. So exceptions to the universal code, as it turns out, are known in a few single-celled eukaryotes and in mitochondria. In those little energy factories of the cell, they have a little piece of circular DNA there. In them, typically circular, it isn't always, but typically circular. And also in at least one prokaryote, that's a single-celled kind of organism. So most exceptions to the genetic code have to do with stop codons. And so here are some examples that I found. I'm sure that since I found these ones, there are probably more that have shown up. And you can see the differences. It's not like the whole, half the words in the codon language are different or something. It's just one or two that are different, but they can be pretty important, quite significant differences. And I'm not going to spend a lot of time talking about why it is that some of these changes, while they make sense in the context of what that organism or those mitochondria are doing, would be very hard to achieve, very difficult indeed to achieve without killing the organism. So they don't look like the sort of thing that you can get in incremental, very small steps, which is one of the things that most people acknowledge is necessary for the Darwinian mechanism to work. Little changes that are then selected. Probably just not the right mechanism to make this happen. Now, I should tell you that these differences in the codons, they're actually a lot more commonly acknowledged now than they were 20 or 30 years ago when I first started looking at this. But when they are acknowledged, they're generally quickly dismissed as, well, but these codons all are just small differences and they're derivatives from that universal genetic code. But that doesn't address in any way the issues that are actually there when it comes to these things. Another thing that occurs with these, if we just look at mitochondria in the major kinds of organisms that we're most familiar with, what we see is there are all kinds of different changes in the genetic code in those mitochondria in different organisms. And I've tried to lay these out on a phylogenetic tree. So this would be like an evolutionary tree that would be what a Darwinist would believe it should symbolize the relationships between all these organisms. And there are many, many difficulties with this. Again, we could spend the whole rest of the afternoon just talking about this. So I'm going to move over it fairly quickly. I just want you to see, hey, there are differences in the genetic code, and they are significant. They're not trivial. I just noted here that if this scenario here is true, and I didn't make it up, this is what would be a typical Darwinian understanding of things. This would mean that AUA, the codon AUA, changed from coding for isoleucine to methionine, Then it changed back to isoleucine in the echinoderms. That's the starfish and animals like that. Yeah, AAA must have changed from lysine to asparagine twice. UGA must have changed to tryptophan, then back to stop again. That's a pretty big one. And generally speaking, when we see these differences in mitochondria, they lower the number of transfer RNAs that have to be made. For those of you who understand how these codons are translated into protein, the information in the codons is translated into protein sequences. So it makes sense. It's just to be changing all these things around like this and survive is pretty much a pretty tall order. Let's put it that way. You're probably familiar with, nice illustrations of DNA as this kind of double helix. But what I've done here is I've kind of zoomed in a little bit to give you a little bit of detail on what's going on in DNA. You remember that I said those words in the DNA language, those codons, they're 3 letters long. So here you can see this chemical up here, that is one of those chemical letters. It's the one that's symbolized with T, because this is DNA. And here is another of those chemical letters here. And down here we have another of those chemical letters. You'll notice that these ones that I'm showing you are all attached to one strand over here on the right of this sugar phosphate backbone that makes up DNA. The other strand of DNA is over here on the left, and you can see that I'm showing you different chemical letters here. It turns out that these chemical letters associate with one another in very specific ways. They form unique bonds between, this is adenine here, and this is thymine over here. Adenine and thymine always match up with one another. And we're just going to zoom in on that. I don't want to give you a whole review of molecular biology, but all this will help you understand the significance of this series of papers that was just published. Here is adenine, and here is thymine. And I'm going to show you why they pair up in a unique way. It turns out that where that hydrogen is there that's attached to a nitrogen on the adenine, the hydrogen just has a little positive charge to it. And oxygen over here has a little negative charge to it. When we go, and what that does is, these opposite charges, they attract one another. That's what these dotted lines mean. It means there is what's called a hydrogen bond between these two parts of these two chemical letters. If we go down here, you can see there's another hydrogen, and unsurprisingly, it has a little positive charge on it. Turns out that nitrogen has a little negative charge sticking out from it. And so there's another of these bonds that is formed. They're relatively weak bonds, but they are important. They're important in this. There are other things, by the way, that go on that cause this base pairing, it's called, between these chemical letters in DNA. But this appears to have some importance to it, particularly in creating the uniqueness of the association between adenine and thymine. This is a different base or chemical letter. It's aminoadenine. And your body, your DNA does not contain this. The DNA of pretty much every other living thing is not known to utilize this different chemical letter. It's actually symbolized with the letter Z. But what you're going to see is how different the bonding is because of this. We've already talked about these bonds that normally exist between normal adenine and thymine. But if you look down at this amine group that is added to the adenine to make aminoadenine, you'll see that there is a hydrogen sticking out there. It has a positive charge on it. And it turns out that that other oxygen that was there all the time on the thymine has a slightly negative charge to it. So when you put them together now, they form 3 chemical bonds. This is huge. This is profoundly different. It has very profound implications for how these things work. It means different polymerases that put their DNA together. It means a different biochemical pathway to make this aminoadenine. It's really an impressive, big difference in the way things work. I'm going to illustrate it just to give you a feel for it by writing my name. So here is my name written in Latin letters. But if I were to write it in Cyrillic letters, it would look, I hope, something like this. You can see that there are some commonalities. I mean, the T and the T there, they kind of look the same. The O looks the same. M looks similar, but you get the point. It's not, the Cyrillic alphabet is not totally different from the Latin alphabet. There are similarities, but wow, that's a profound difference. If I'd written everything in this presentation using the Cyrillic alphabet, even though I would have been using it to write in English, you would have had terrible trouble understanding it. And that is precisely the kind of situation that exists with DNA if you substitute the aminoadenine for normal adenine. It is a really big change. It's a really big difference. It's not something that you're going to get with slight gradual changes over time. That's just not going to happen. So what are the implications of this? Viruses are technically not living organisms, but they use the systems found in living organisms to reproduce. That's why SARS-CoV-2, which causes COVID-19, is such a big problem for us. It gets into our body and it gets into our cells and it takes them over and uses them to make copies of itself. And by doing that, it causes severe illness in many people. The viruses that we're talking about here, by the way, only infect bacteria, and that's going to be important here. Using a different alphabet is thought to protect those viruses that use aminoadenine from some defense mechanisms found in bacteria. So they're that different that these bacteria don't have mechanisms to shut them down. A big problem for bacteria, thankfully not for us. So the idea that the universal genetic code supports common ancestry is an overstatement of reality because the genetic code clearly isn't completely universal. Okay. But what happens when we throw this into the mix? First of all, let me just say as an aside, we probably need to rethink viruses. It turns out that they're a lot more interesting than we thought they were. There's a lot going on there with viruses. And yeah, we need a new conceptual framework probably for them. I'm not arguing that they're living organisms or something like that, but they're just different than the way we've traditionally thought of them. Going on here, the use of significantly different genetic, a significantly different genetic chemical alphabet by some viruses raises even more questions about how compelling arguments about the genetic code or genetic systems are when based on the idea that they're all the same. Obviously, I mean, this is just profoundly different, what's going on in these viruses. You know, yeah. Also, these papers demonstrate just how surprising nature is, especially biology. You know, it's one of the reasons I love being a biologist. And you've probably heard people talk about, you know, people saying, oh, well, you know, everything you've learned in university, half of it's not going to be true. But the problem is I can't tell you which half isn't going to be true. I can tell you that my personal experience has been that, yeah, you know, not only did I feel like I knew nothing when I graduated with my PhD, I feel like I know less now, just because so much has changed. So much that I thought I did know then turned out to be so much more interesting than we thought it was at the time. And this is a great example of that. You know, nature is going to keep us entertained for a long time. Final paper, and this one's a quick one: the genomics of rapid climatic adaptation and parallel evolution in North American house mice. So this is talking about European house mice that are here in the US. The European house mouse arrived in North America about 200 years ago. And so it hasn't had a lot of time to do much evolving here, you would think, and yet there's been evolving going on. Those in the cold north and warm south show clear adaptations to the different climates where they live. In this study, body weight, nest building behavior, metabolism, and temperature sensing are noted. So they're looking at those sorts of things, and quite predictably, really, mice that are found up in the north, where it gets quite cold, tend to be significantly larger than mice found down in the south, where it's generally quite warm. And this is to be expected, because the smaller you are, the more rapidly you can dissipate heat. And so if you're hot already, getting rid of heat is a good thing. So being small is good. Whereas if you're up where it's really cold, you want to be bigger, because then you dissipate heat much slower. There may be other advantages as well. That's just one example of how this works. So it's believed that mouse colonization of the eastern United States occurred independently of colonization of the West. So the mice on the East Coast and the mice on the West Coast, they're not directly related. They came from different introductions. And because of this, adaptation to different conditions had to occur independently. So the ones that evolved to survive in the cold north in the east, and the ones that evolved to survive in the cold north of the west are not related to each other, at least in the recent past. So they had to evolve those adaptations quickly, right? So when they went and examined mice in the east and the west, they found that they exhibit the same phenotypic and genotypic adaptations to warm versus cold climates. So as long as you're just looking at the temperature, the adaptations, the changes that are observed are the same. While they exhibit differences where that reflect environmental differences between East and West as well. So the surprising thing here is the sameness, those traits that are the same, because you would think that evolution has many different paths that it could be exploring to adapt to different things. In fact, that's one of the sort of arguments that's made, you know, different things happen and you wind up with different species. This is what the paper says. This is a quote from it. There is significant overlap between genes under selection in eastern and western house mouse transects, so where they're going from north to south, providing evidence of parallel genetic evolution in response to similar selection pressures across North America. This actually has some really important implications, and I hope that I summarized them well. The process of evolution in which organisms adapt to local conditions is not purely random. So, you know, the idea is that natural selection acts on variation that occurs within a population of a specific organism, but that variation is generated by random changes to the DNA, random mutations in the DNA. But when we look at these things in detail, not just in the house mouse, by the way, but in bacteria, hey, in the SARS-CoV-2 virus that causes COVID-19, we see this. We see that certain mutations show up in certain places much more frequently than other mutations. And that frequently seems to have some importance in adapting organisms to a different environment. Organisms will commonly exhibit the same genetic changes under the same conditions, suggesting that mutations that lead to these changes are not necessarily random. If we were relying just on random changes, it would take a very long time for populations to adapt to their local environments. But what we see is very rapid adaptation. We see organisms, if they can survive at all, they'll be stressed and their mutation rate seems to increase, but it's not just a random mutation rate that's going on. It seems to be focused on areas where changes may help adapt the organism to that local environment. What we don't observe is them then going on forever and turning into some other kind of organism. When they evolve, it's fast and then they stop. They don't just sort of keep evolving off in some direction forever. If some mutations are more likely than others, and that appears to be the case, And those that are more likely just happen to adapt organisms to environments that they were not previously well adapted to. This does not look like unguided randomness. It looks like design anticipating that organisms will have changing needs in a dynamic world. So in one sense, it is evolution. It's certainly adaptation, but it is not speciation in the sense that Darwinism refers to it. It looks like a pre-designed mechanism to allow the rapid adaptation of organisms to this changing environment that they find themselves in. Francis Crick, and again, I want to stress that I'm not wanting to make fun or insult the people whom I'm quoting. Okay, I'm using them to illustrate the thinking that is out there. It happens to be thinking that I disagree with. But Francis Crick, who got a Nobel Prize for figuring out that double helical structure of DNA, wrote, biologists must constantly keep in mind that what they see was not designed, but rather evolved. Keep in mind, Francis Crick was an atheist, and this is what he believed, but this is a religious statement. It isn't that the biology actually compels this belief. It's that the belief compels this understanding of biology, one that I think is very unfortunate and untrue. So beliefs obviously can blind people to what is actually going on out there in the real world. This is a text from right at the beginning of the Bible. God has just created the fish and the birds, and God blesses them, and he says this, be fruitful and multiply and fill the waters in the seas, that's obviously to the fish, and let the birds multiply on the earth. There's this idea in the story of creation that organisms are to go out there and fill the earth. But if they're going to do that, they are going to encounter different things. It looks, if we consider this particular paper about the mice in North America, it looks as if God designed organisms with the capacity to rapidly adapt to new environments as they encounter them. And so that they have the capacity to fulfill this particular command. Of course, I should stress, I personally, as a Bible-believing Christian, do not believe that the system was the same when God created things. So everything wasn't achieving this through death and so on. But somehow or other, it looks like God put these mechanisms into organisms. They rapidly adapt, but they don't go, lions do not turn into oak trees or something like that. You just don't see that kind of thing going on. And I will end, I think, with this text. Happy is he who has the God of Jacob for his help, whose hope is in the Lord his God. Okay, so who is this God? It's the God who made heaven and earth, the sea, and all that is in them, who keeps truth forever, who executes justice for the oppressed, who gives food to the hungry. And these next two lines in this poem really captured my attention. The Lord gives freedom to the prisoners. The Lord opens the eyes of the blind. I sincerely believe that Darwinism blinds people to what's actually out there, the beauty and the wonder and the marvel that is life on earth and the universe and everything. What the biblical worldview does, what Christianity does for people, is it liberates them from that imprisonment within this materialistic philosophy that says it doesn't matter how designed it looks, you may not believe that. It blinds people to what is right in front of them. The Lord raises those who are bowed down. The Lord loves the righteous. And certainly one of the ways in which that love is expressed, I believe, is in the creation that he made. Okay, let's see here. That is the end. And so I hope that I haven't bored you. I hope that I've been able to open your eyes a little bit. I hope that my explanations were clear enough and simple enough that anyone could understand them. I know it's easy to get bamboozled with some of this stuff, but we'll find out. So if you have questions or comments, I would be delighted to hear them.
Thank you, Dr. Standish. That was fascinating. If people do have questions, they can either type them in or I will allow people to unmute. Just give me one moment here. Now people can unmute themselves if they would like to ask a question.
You see, this makes me very nervous. It makes me think that I might have just bamboozled everybody.
Well, I'm no scientist, but I was following the implications of these discoveries, and they truly are a challenge to the traditional evolutionary worldview. So
they should be, and yet, you know, that's one reason why I gave those examples of how the very people who are publishing these things, because they're trapped, really, in my opinion, in this view of things, it really truly blinds them to the implications of what they're doing, which is extraordinarily unfortunate. You know, I should say I wasn't completely lying when I wrote the abstract for this originally. There are just dozens of papers that have struck me just in the last few months. Really profound stuff. The genome of the axolotl was published. This is a kind of large salamander, and it turns out to be massive, you know, over 14 billion bases. So, you know, all those ATs, Gs, and Cs, your mother gave you about 3 billion of those. This creature, its mother gave it 14 billion of them. And yeah, just, I mean, that's how many meters worth of DNA in every cell. It's somewhere between 6 and 8 meters. Well, no, it's a little less than that. The bottom line is we're talking about many meters worth of DNA in every single cell of this thing. Lungfish, by the way, they're in Australia. are supposed to have the largest genome. They're pushing, I believe, about 15 billion. Just that's a huge amount of DNA, and it all has to be folded up very specifically inside every single cell, so it doesn't get all tangled up and whatever in these tiny little cells. They've got all these meters of DNA in there. Quite an incredible thing. And they are supposed to be the ancestors now of all organisms that walk on land. Everything with 4 legs, basically, including you and me. Somehow or other, we wound up, and everything else wound up with a whole lot less DNA, and they got the mother load. It's hard to understand necessarily why. But, and in another incredible paper about bacteria, bacteria are supposed to evolve relatively fast because they're small and they reproduce rapidly and everything. And we can observe them to do it. There are certain things, like they can develop certain kinds of antibiotic resistance very rapidly. But they don't turn even from one bacterium into another kind of bacterium. They're the same kind of bacterium. They're just immune to a certain antibiotic. The amazing thing is, when they put these really deep wells down into the ground, there are bacteria way down there in the rocks. So someone thought, hey, you know what? If we do that on one continent and see what bacteria are there, and we do it on another continent and see what bacteria are there, we should find, some really significant differences because, well, evolution. So what did they do? They got these 2 species of bacteria that happen to live way down there from these different continents. They turned out to be identical. And obviously, if you're a bacterium and you're a few kilometers down in the ground, you're not exactly moving around real fast, and you're not crossing oceans and doing that sort of thing. These things are supposed to be separated by hundreds of millions of years, or at least tens of billions of years. They've done nothing. In the time that something resembling a wolf is supposed to have turned into whales in less than 10 million years, and yet these bacteria, no changes. Just sort of a very interesting paper, confounding, really. So much stuff out there. Another one. See, no, I want you guys. I'm going to stop talking because I want you guys to ask some questions. I have all sorts of interesting stuff, but I want to know what you're thinking.
Is there a place where people can find these discoveries, these new papers? Is there a place where people can go to be updated on the latest in these?
There are multiple services that sort of give a news summary of many papers as they come out. Eureka Alert would be one. Science Direct is another one. There are services like that. On the Geoscience Research Institute webpage, and the URL for that is grisda.org, so grisda.org. You'll find that there is a news section where we will frequently just list relatively recent papers that you can access that have some implications. Now, I should warn you, we don't only put papers up there that make us look right and everybody else look wrong. So it's papers that we consider to be important in this area of origins, whether they agree with our position or they're disagreeing with it. Yeah, thanks so much for putting that up, Iman.
Thank you. I believe we do have a question from Josh.
I've got two questions too.
Okay, let's go to Josh and then to Daryl.
What animal has the least amount of DNA in it?
You know what? I don't know what animal has the least DNA in it, but there are a lot of experiments that are being done to try to figure out what the absolute minimum amount of DNA is that you can have in an organism. And it used to be, now they're trying to make basically artificial organisms to see who can hit that rock bottom. But it used to be that an organism called, a little bacterium called Mycoplasma genitalium was generally accepted as the smallest. It has about 300 and something genes in its genome. Off the top of my head, I can't tell you the length of it, but it's in the thousands of nucleotide bases long.
Okay.
So it's very, very small. And I should also point out that is not really an independently living organism. It's a parasite, and parasites tend to have everything stripped down. Yeah, so Mycoplasma genitalium would be a good place to start if you wanted to Google that and sort of find out a little bit about it. With artificial genomes, what they've actually tried to do is see, okay, we've got this organism with this bacterium with a very small genome. What happens if we chop out this little bit here? All right, if we get away with that, then we'll try chopping out another little bit. But they seem to have hit a brick wall somewhere just below 300 genes to get something that is capable of even the most minimal survival and reproduction, with everything it needs sort of being fed to it. It's not something that would survive in the wild in any way. And to give you an idea of how blurry the edges can be on that, there was a paper that came out this year that was talking about this, and they'd managed to get a bacterium that would divide, but as it divided, it didn't do a good job of it. It wouldn't equally split into two new cells. And so it was a very sick bacterium. And they wanted to ask, how can we get this thing to divide properly? Just split the cell into two equally sized cells. It turned out that took addition of something like 15 additional genes just to get that one thing to work. So, which is the smallest genome? The genome of the one that can actually divide properly by itself, or the genome of the one that could sort of survive on life support all the time? Yeah. So that's why there's a little bit of a blurry edge to that. Good question. And by the way, it does inform the question of origins, because it tells you where the rock bottom is. You know, how much genetically encoded information do you need to have to start everything rolling in the first place, if you believe that everything started with one bacterium and evolved into you and blue whales and stuff. That's the minimum starting point from a materialistic sort of Darwinian thing. And while, you know, about 300 genes doesn't seem like very many, it turns out that, first of all, chemistry isn't going to do that for you. Secondly, even if you did have some kind of miracle that allowed these things to start assembling randomly, there just is no remote possibility that this is an event that occurred in the history of the universe. Just not there's not what's called the probabilistic resources available for that. So.
Thank you, Daryl. You have a question?
Yeah, question. Question number one. Just interested in knowing how you're going, Dr. Standish. What time is it over there?
It is 10:26 p.m.
Oh, that's not too bad.
No, it's not too bad. No, trust me, I've done far worse. I can tell you that in my job, for reasons I don't fully understand, you know, there are occasionally these global meetings that we have to attend, and somebody has decided that the best time possible is 7 a.m. on the East Coast of the United States, which happens to be 4 a.m. for me. So there's been some pretty rough early mornings.
All right, second question. There has to be very good reasons why God designed the eye and the light receptors, etc., so that they're at the back of the eye and see things upside down, etc., etc., etc. And I'm a little bit intrigued as to the likes of Richard Dawkins, who are happy to acknowledge that this must be some sort of defect in the design process and very poorly designed. Have they been able to come up with what they consider a better design for human eyes and the way that they work?
I believe, you know, I can't really speak for Richard Dawkins. I'll try to channel him for you, okay? And I'll try to be fair. If you look at the retina design in squid, you know, which have a camera type eye like ours, their retina is designed the other way around. And I believe that Dawkins would say that is better. The problem is, while it works okay for squid, it would be vastly inferior for us. See, our eyes very, very, very rapidly refresh the image that we're looking at, or that we're detecting. And the squid eyes do not do that in that way. So they have lower, squid's eyes have much lower metabolic demands. So that's one reason why their blood supply can be significantly less. They're just doing it. They're great eyes for squid. They're just not, they would be the, in the eye world, they would be the equivalent of, you know, a donkey cart. It might get you to where you want to go and actually be really much better if you don't have gasoline. But what we have for eyes are Ferraris. Totally different thing. And if you want to get from A to B and you have nice paved streets and lots of petrol, a Ferrari is a great way to do it. So that would be sort of an analogy of what's going on there.
Darwin himself said that the eye was something in humans that frightened him.
Yeah, you know, it's interesting. I don't know. Do you ever look at the John 10:10 project videos? Google the John 10:10 project and take a look at some of those videos. The latest one that we just put up there actually uses that quote. And on our Facebook page, the GRI Facebook page, we got the usual trolls that are always there. And one guy was saying, I don't believe for 1 minute that Charles Darwin made that statement, you know, but we used it because we'd used it in the film. Well, you know, in the information age, it takes precisely, 10 seconds to put a quote in to see whether it's genuine. But what it does is it just sort of reveals the dogmatism of people. Darwin's followers are more dogmatic than Darwin. And trust me, Darwin was pretty dogmatic. It's quite amazing. It's sad to watch it. I'm certainly not one of those people who thinks everybody has to agree with me about everything, or that people who disagree with me are necessarily stupid or something. But there's a certain sadness to present people with evidence that has very clear implications and to have them just, you know, effectively stick their fingers in their ears and close their eyes, and cling to their idols, if you want to put it that way.
Thank you.
Hey, thank you.
Well, I'm not sure if there are any other questions, but we don't want to keep you up too late in case you do have another early meeting coming up in the near future.
Thankfully, there's no waking up at 3 a.m. for me tomorrow.
Good. Well, you need the rest anyway.
Thanks.
And yeah, very much grateful for what you have shared with us today, and we look forward to having you in person.
That's right. Let's do it in person next time. I don't know when I'll be able to get back to Australia in any sort of convenient way. I did do the 2-week, you know, thing here a while ago. It's not pleasant. It's not as bad as some people make out, but it's not something I think any rational, reasonable person would choose to do.
Well,
it was very interesting, Timothy. It was very interesting.
Well, thank you very much. You know,
I appreciate it. I really appreciate the time you taken so much. Not it's need to be very patient to follow all the links and get to understanding, truly understanding. It's very easy to misunderstand, and it's a pretty terminology, all chemistry. That's what I.
Yeah.
It's a great effort, Timothy. I appreciate it once again.
Well, thank you so much. It's my pleasure to do this sort of thing.
Yeah, it's a great time. It's a great effort to put it through in coordinate everything. Oh wow, it's a big project. It's an ongoing project.
Yeah.
I wish you all the best.
Thank you very much.
So I'll see you in near future.
That's the case.
All right. You have a good night.
Thank you.
Happy Mother's
Day. We wish you
Happy Mother's Day.
Yeah, thanks.
Yes, happy Mother's Day to the mothers. And we we wish you a good evening, Dr. Standish, and a good afternoon to those who are here in Australia.
Good to see him.
You too. Okay.
Thanks so much.
Bye.
You guys have the rest of your Sabbath. I hope it's a happy one.
Thanks.
God bless.
Thank you.
Yeah, you too. Happy Sabbath. Yes.
Goodbye now.
Bye.
Thank you.